Frictional resistance will be in any direction. We can say the frictional resistance is equal to mu into the normal force. Mu into the normal force. So that normal force is cos theta. Weight is this one, so reaction will be like that, and then it is mu into cos theta. Okay. So this mu cos theta is basically opposing these forces. Now I'm not drawing exactly the direction here, but we can say that this is say mu cos theta. Now what is mu? That is, again, we need to refer to the frictional property of the soil. Okay, so but let me write here as mu cos theta. Here itself I am showing. On this face it is easy to show, and here just I am drawing it because that is, we cannot see the back side from this side, that's why I am drawing it here. Well, so this is equal to mu cos theta. Resisting force F2, if I write, this is equal to mu cos theta. Now if angle of internal friction of the soil is say phi, then what the mu is, that we all know that mu is nothing but the tan phi. If the angle of internal friction is phi, then it is tan phi. So we can write that, this is not cos theta, this is w cos theta. This I did a mistake in writing here. This is not cos theta, this is w dash cos theta. Again, dash is always coming, w dash cos theta. This effective weight of the soil will be significant there. So this will be, this I should write as mu w dash cos theta. Okay. This will be w dash cos theta. Well, and this mu we can write, as I have explained, that this is equal to tan of phi to w dash cos theta, where phi is nothing but angle of internal friction, angle of internal friction. Well, so now for incipient motion condition, we can equate these two. So equating these two, what we can write, that w dash cos theta and tan of phi, this is what the resisting force, and the other one is say tau s a plus w dash sine theta with a root sign. Then squaring these two, what we can write, that w dash square cos square theta tan square phi is equal to tau s a. Just to, our target is to separate this tau s, and then this is the tau s square s square. These were also square because after taking square only we were taking the root. So it will be tau square a square w dash square sine square theta. Well, now this expression where we got is this one, tau square a square dash square w dash square sine square theta. We are writing the same expression here. Okay. Then from here what we can write, that tau s is equal to, that is the side tractive trace, we can write from this part as w dash cos theta tan phi by a. first we are writing tau s is equal to this minus that, and then we are taking w dash cos theta tan phi common, and then of course we are taking root, and then if we take the other part here, then it becomes 1 minus tan square theta by tan square phi. Well, so when we took tan phi common, then here we are having already, say, tan square phi is coming here, and then it becomes, and we are taking cos theta common, so it is becoming, in fact we took cos square theta, so that way it is becoming cos sin square theta by cos square theta, so this tan square theta is coming, and then later when we took root over, this cos square theta become cos theta, tan square phi become tan phi, and all are just getting this. Just one more step we could write in between. Well, so that way we are getting this tau s, the side attractive force. We are getting an expression. Let us give a number 1 to this equation. Well, now if we talk about the shear stress at the bed, so shear stress, or rather let me use the word unit tractive stress, unit tractive stress or tractive force, unit tractive force, because already we are using the term unit. So tractive force at bed. Now what is the difference between this particular expression in bed and side? Well, if we talk about bed, then our theta for the bed is becoming 0. If we just flatten it, this becomes bed. So in bed, other things will be remaining same. This force will be there, the reaction force will be there, but here if we take a bed, same area, then this force will be there, and this is tau b into a, then weight component will be directly vertical, so there will be no component in that direction, and then the resistance force will be coming here. It is directly equal to W, means basically if we make theta is equal to 0, then we get the expression for bed. So what we can write, unit tractive force at bed, tau b is equal to, so if we make theta equal to 0, our expression will become, say, we can write it as W dash by A. We can write W dash by A, and then on the W dash by A, and then it is tan of phi. Okay, this part means W dash by A cos theta is becoming 0. Theta is becoming 0 means cos theta equal to 1, and then it becomes tan phi. And what about this part? When theta becoming 0, this part is becoming 0, and that's why it is 1 minus this, means only root over 1. So finally this is becoming 1, and we get this expression. So this is what the expression 2. Now our target was to find an expression or to find a relation between the shear stress or unit tractive stress, attractive force at side, and unit tractive force at bed. So we can now do 1 by 2. So that will give us, say, tau s by tau b. Tau s by tau b is equal to this, and that part will get cancelled, and we will be getting only cos theta, that root over 1 minus tan square theta by tan square phi. Well, so this is what very important expression that we use for design purpose. And then as you can see that cos theta root over this can further be simplified, but of course we are leaving it in this level, that is tau s and this ratio. This ratio has a particular name. We call this as a k. We call this ratio as a k, and then what we can see that k is equal to, say, tau s by tau b. This is equal to cos theta root over 1 minus tan square theta by tan square phi. That is name we are giving as k. And then one point we should note here, that theta will always be having some value, and of course for trapezoidal channel, and then this value will be always a fraction, less than 1. So tau s is always equal to some fraction multiplied by tau b. Well, what it means, so this ratio we name as k, and so you can see that k is tau s by tau b and cos theta root over 1 plus tan square theta by phi. And more importantly, that when we see that cos theta value will be always say a fraction. So it is between 1 and 0. So it will be a fraction, and cos theta value will be a fraction. So the highest being 1. Now so if this is a fraction, then what we can derive from that tau s by tau b is always a fraction, because tan theta by tan square phi, this will be of course a positive term and less than 1. So 1 minus something less than 1 and root over terms. So this product will be, okay, whatever it is, this thing, that this product will be a fraction, and that way we will be finding that this tau s is equal to some fraction multiplied by tau b. And that way we are getting the tractive force at side is less than the tractive force at bottom. Tractive force at side is less than the tractive force at bottom. And this is very important, which help us in proceeding for design. Well, now let us just see how we can have now let us talk about design of tractive force method, or rather design by tractive force method. And till now we have discussed about tractive force, that is how we can have theoretically a relationship between the tractive force at the bed and tractive force at the side. And that way, once we can have some idea about the permissible tractive force at the bed, then we can know what will be the permissible tractive force, unit tractive force at the side, permissible unit tractive force at the side. So this is we have done, and we can get it. Then how much is the tractive force exerted by the fluid on the side and bottom bed of the channel, that we can get from the curves given by USBR. Well, now let us see how these informations help us, in designing the channel by tractive force method. Well, and for design purpose, we define few terms that are important. We call this as a critical tractive force. Well, so what is critical tractive force? The tractive force at which the particles are just in incipient motion condition. This is called critical tractive force. Well, then definitely we do not design in engineering any design for the critical condition. We do it for a situation that it is safer or better than the critical condition. We are not generally try to reach the critical condition. So when we talk about permissible tractive stress or say permissible unit tractive force, then we define it in a way that permissible tractive force is kept less than the critical tractive stress. Well, and now for what type of soil, what will be the permissible critical stress? This is very, very critical. This is really critical. I mean, we have theoretically derived one relationship between the bed tractive stress and side tractive stress. That is fine. But what will be the critical tractive stress for the bed or for the side? What will be the limiting value? That is a very difficult task. And why it is difficult? Because, say, we are talking about alluvial channel, but there also will be some finer fraction, and those finer fraction will be changing the value. And then it is of course generally expressed in terms of the diameter of the particle. It is generally expressed in terms of the diameter of the particle. So if diameter of the particle is this much, then tractive stress required is this much. In fact, when we did discuss about the uniform flow in erodible channel, then we were studying those aspects also. We were discussing seal theory, and there we were discussing those aspects. But again, say particle size only doesn't matter. Sometimes the orientation of the particle, then what is the shape of individual particle, how is the frictional resistance, all those factors will be influencing. Well, compactness and other things are also coming into play. So like that, this derivation of this tractive force is difficult, but still for our purpose that we need to design, so we'll have to follow some methods, and the experience has shown that, well, this approach, if we follow, it gives us a suitable channel which we can use for our purpose, and it is stable. So that way we go by those methods. In fact, USB are also conducted a lot of experimentation, and they gave a very quite convincingly they could give the value of permissible tractive force for a bed based on the particle diameter. And that relation, what they gave is the tau b, and of course they gave in pound per feet square, is equal to 0.4. Its relation is very simple, 0.4 into diameter, and that diameter is in inch. Diameter is in inch. And now in India we are using, say, diameter in millimeter or say centimeter we'll be talking about, and then we are not talking about pound per feet square, we may be talking about Newton per meter square, kilonewton per meter square. So that way, if we use this equation, then this relation, then we need to convert the unit, and this is well known how we can convert from inch to centimeter. Just to give readily how we can have pound per feet square to kg per meter square, that we can convert as 4.882 kg per meter square, 1 pound feet square is equal to that we can have. And if we want to convert it to Newton, then we multiply it by 10, like that, kilonewton, 1000, so like that we can change these things. Well, so that way we can have the value of, say, tractive force at bed of the particle, at the bed of the channel, by using the relationship given by USBR. Okay, this is directly giving us permissible tractive stress. Well, but again, as we have just discussed, that we were discussing Seals theory also, and then from Seals theory we got a curve, and from that curve ultimately we could derive the tractive stress, or this we gave as critical tractive stress, tau c we were writing by Seals equation, and there with tau c, if we keep in kilonewton per meter square and say diameter of the particle in meter, diameter of the particle in meter, say d diameter in meter, and tau c is in kilonewton per meter square, then we could see that Seals equation gave us a relation like 0.06, then unit weight of water, the g is the specific gravity of the soil, and then -1 into diameter of the particle. That simplified equation we could get. And that equation, if we simplify further by taking the standard value of W and by taking the standard value of say soil, maybe 2.65, like that, the soil specific gravity, then we can get a value tau c is equal to nearly 0.98 into d. Okay. Well, then White equation is another equation that gives us critical tractive force or critical tractive stress tau c as 0.801 into diameter. The unit is same. And then Lenz equation is another equation which is generally applied when the flow is when it is a fully developed turbulent flow. In that case, our tractive force is at little lesser tractive force, the particle starts moving for a fully developed turbulent flow, and then tau c is given as 0.78 into d. So these values can also be used for determining the permissible tractive force or permissible unit tractive force or the permissible tractive stress at the bed. And what is that? That is, permissible tractive force can also be taken as 0.9 of tau c. Here we are getting tau c. And then by this method, if we calculate the value and then we take the 0.9, that is 90% of that value, then that we can take as permissible tractive stress. And then if you just try this calculation, then from this calculation, if we do, if we just try this calculation putting for standard values, then we find that we get almost expression of 0.76D. This will also ultimately lead us to a value. If we change this unit, it will lead us to a value of the 0.76D around. And then here it is tau c, and then we need to take 0.9 time of that. So more or less we are at almost